using the Muller method. So what we need to find is we need to find the approximation x3 for this polynomial equation. We will start from x naught x naught x1 x2.
So we cannot hear.
Muted actually. Okay. Thank you for reminding me. Okay, so um, previously I told that the Muller method was mm, okay. So previously I showed that this was the Muller method. I have as, uh, input this Muller method on this Moodle, and then how to apply this method on Excel. Okay, so how to set up this method on Excel. So you can have a look at this so from here in from Moodle. So you can have a look at this method. Okay, so now today we are going to discuss about the Bairstow's method. Okay, which is the second method. So in the Bairstow's method is an interactive approach loosely related to both Muller and Newton-Raphson method. So the steps of the Muller methods are as follows. So we start from this equation, okay? A naught plus A1 x plus A2 x square plus AN x power n. So this is the standard form of the polynomial equation of order n. Okay. So can you see this slide and can you also listen me?
Yes.
Yes.
Okay. Then I am going to now I am explaining the Bairstow's method. So what we would do, we want to find the roots of this polynomial equation. However, the methodology of the Bairstow method is that we take a factor of this polynomial equation in the form of a quadratic, and that quadratic is x square minus rx minus s. Okay, so if, for example, if we take this equation and if we divide by this quadratic, which is the root of this, which is one of the factor of this polynomial, then the remaining polynomial is 2 degree less than this. For example, if this is a polynomial of degree 4, and then we divide it by x square minus rx minus s, so we will get a quotient that will be 2 degree less. That will be in a degree of 2. Okay, where r and x are special coefficients for this polynomial, for this quadratic. So this will be the resulting equation. Okay, after you divide it, this will be the resulting equation. So this resulting equation will be with a remainder of this. Okay, if it is this remainder will be 0, if x square minus rx minus s is a factor of this polynomial. And if it will not be zero, then the value will can be determined by this. So here, here you can see that this new polynomial is in terms of the coefficients b naught, b1, b2, b3, etc. Okay, and uh, the original polynomials are in terms of the coefficients a naught, a1, a3. So if the original polynomial we have, so we know the values of a1, a naught, a1, and up to an. But then we need to find the values of b2, b3, bn if we want to further factorize this polynomial for finding the root of this polynomial. Okay, so we need to find the values of b naught, b1, and up to bn. And then how we can find the values of b naught, b1, b3? This is provided by the results of the Bairstow's method. So the results of the Bairstow's method shows that the values of these coefficients the values of these b coefficients can be found by these equations. So Bn will be equal to An, where n is the degree of the polynomial. So if the degree of the polynomial is say 5, so we will start from 5. So B5 will be same as A5. Okay. And what was A5? A5 is the coefficient of this nth order uh, nth order term in the original polynomial. And then one less there of that bn will be b4. Okay, so b4 will be equal to the a4 plus r times bn. Okay, it will be plus r times bn. So r is this value which by which we are dividing this polynomial, and b r times bn, that means uh, uh, sorry, that means the bn, that is the previous value which of b which we have found from here. And similarly for other polynomials uh, from bi to b0, that means for the values of I from n minus 2 to 0, that means if n is 5, n is 5, so for I, the value of I from 3 to 0, we can find the values of b3, b2, b1, and b0 by this formula. So it will be ai, that means b3 is equal to the a3, and plus r times uh, b4 plus s times b5. Okay, so and where b4 and b5 are these previous terms over here. Okay, in case when we take n is equal to 5. So in this way, systematically we find the values of these coefficients b. In addition, we need to find these coefficients c as well. Okay, and these coefficients these c coefficients we will also need. But the difference is that their formulation is the same as b, is on the same pattern as b. So just as bn is equal to an, so cn will be equal to bn. So the coefficients of c will depend on the values of b, whereas the coefficients of b depend on the values of a. So from a we will calculate b, and then from B we will calculate C. But there is one difference, whereas we need to find the values of up to B naught, okay, to B n. But here we will not need to find the values of C naught, okay? There is no C naught coefficient. There is only the coefficients C is from 1 to n, not from 0 to n, okay? So that's why you can see that for I is equal to n minus 2 to 1, okay? Otherwise, the formulation of C is same as for B, okay? So for C4, we will take B4, and then we will take R and then multiplied by Cn, okay, which is the previous term. So, and also you can see that, and what will be the R and S? R and S will come from the factor with which we will be dividing it. Okay, so x square minus rx minus s. This is the quadratic factor. Okay, so in other terms, r and s will be our initial estimates. Okay, so they will be iterated. They will be iterated. R and s will be iterated. Okay, so simply so again, the steps of the Bairstow's method is that we have the polynomial equation. We take a quadratic factor, and then from this quadratic factor, as a first step, we calculate the b factors, okay, b coefficients, and then we calculate the c coefficients. And the next step is solve this equation in terms of delta r and delta s. So this is a set of two linear equations, a system of two linear equations in delta r and delta s. And then delta r and delta s, the coefficients are C1, C2, and C3. C1, C2, and C3, okay? So we need C1, C2, and C3, these coefficients for solving delta R and delta S, okay? And remember that we have already calculated these coefficients C, which all depended on the coefficients B. And on the right hand side, we have the B1 and B0, minus B1 and B0 as the equation. So once we calculate this delta R and delta S, then this delta R and delta S will provide us the change in the values of the these R and S initial estimates. And from this change, because delta is for the change, so from this change, then we can calculate the R and S for our next iteration. R and S for our next iteration. So we take delta R and then we add with R, and then that will be the R for our next iteration. So in this way, then we can calculate the uh, uh, percent approximate error, okay, for R. And then we also calculate the percent approximate error for S. So when these percent approximate errors in R and S are within the stopping error limits, so then we have approximated or iterated the method to our desired level of precision, precision or accuracy. Okay, so then we can stop the process. Okay, so after we have determined the values of R and S in this way by an iterative method, okay, by an iterative method, we iteratively determine delta R. We have to repeat this process, okay. Then we can find the estimate of the root by this equation, okay. X is equal to R plus minus square root of R square plus 4S over 2. So this is the same, and this is the quadratic formula for the equation, for this equation, okay. Originally we assumed this equation. This is, so if you use this equation, uh, if you use this factor as a quadratic equation, and we can apply the quadratic formula on that, and then that quadratic formula will give us the solution in this form, okay. Quadratic formula will give us the solution in this form. Okay, so x is equal to R plus minus square root of R square plus 4S over 2. So at this point, there are three possibilities. So the quotient is a third order polynomial or greater. So the previous values of R and S serve as the initial guesses, and Bairstow's method is applied to the coefficient to evaluate the new R and S values. So remember that after you apply this method, for example, for a fifth degree polynomial, so from the fifth degree polynomial, we will get a third degree polynomial. And then we can apply the same method on the third degree polynomial. And then from the third degree polynomial, we will get the first degree polynomial or the linear equation, and which we can solve by the direct methods. Okay. So this was the method, and then let's illustrate this method with the help of the example. So this method, Bairstow's method, can be used for finding all the roots of uh, the polynomial equations of higher orders iteratively, and it also includes the both the real and complex solutions. Any question you want to ask about this?
No questions.
Okay. So let's see how we can apply this method to solve the equation x power 5 minus 3.5 x power 4 plus 2.75 x cubed plus 2.125 x squared minus 3.875 x plus 1.25. So this is the polynomial which is given, and you can use any values of r and s. Okay, so just for in this case, the initial guesses of r and s are -1. Okay, r is equal to -1 and s is equal to -1. And the stopping error, just say, is 1%. Okay, stopping error is 1%. So what we can do is, first of all, we can calculate these coefficients. So this is the main step actually. So we will calculate B5, which is equal to A5, okay? And then we will calculate B4, which is equal to, so for example, by applying these formulae iteratively, uh, by these formulae, then we can calculate the coefficients B and C, okay? So in this way, you have calculated B5, B4, B3, B2, B1, and B0, okay? Then we calculated C5, C4, C3, C2, and C1. So this step normally takes time in the for hand calculations, but it will be easier if you, because many of these formulae are similar, it will be easier if you can create a table of this. So for example, table of B values, table of C values, and then we can see that we can very easily calculate the values of B and C. So the values of B will be calculated from A, and the values of C will be calculated from B. Okay, so suppose you have calculated these values, and then we will apply this equation. That means apply these values into these equations. So for the application of these values into the equation, we only need C1, C2, and C3, and then B0 and B1. Okay, so C1 to C3 and from B0 to B1. So we just input these the values which were found. So this is C2. So C2 was here. Okay, and similarly C2 is here, and this is C1, and then this is C3 over here, C3, and then minus B1. Yeah, this is minus B1, and then this is minus B0, minus B0. Okay, so this is a set of equations, delta R and delta S. So we can use any method to solve this set of equations, such as the Cramer's rule. So in the Cramer's rule, what you have to do is, if you want to find the value of the delta R, so you will replace these 4.875 and 16.375 with these 10.5 and minus 11.65. So in place of this, you will place 10.5 and 11.35, and then you will find the determinant by the cross multiplication. So that will be 10.5 minus 11.375, and then plus 10.5 minus 10.5 into 10.75. So that will be delta R divided by this main determinant. Okay. So you can apply the Cramer's rule to find the delta R and delta S in this way. So suppose we have applied this method, and we will find that the delta R will be 0.3558 and delta S will be 1.138 in this case. Okay, and then from this delta R and delta S, we can find the revised values of R and S, because initial values of R and S were -1 and -1. So for a more accurate solution, the value of R should be changed by 0.3558, which is given by this value of delta R, and the value of S should be given by 1.1381, which is given by delta S. So after changing this, the new values of R and S will be minus 0.6442 and plus 1381. And the next step will be to find their approximate errors. Okay, so the approximate error will be delta R over the new value of R, and the delta S over the new value of S, all represented in absolute terms, and then multiplied by 100. So in this case, we found that the approximate errors are very high. So 55.23% and 824.1%. So these values are very high, but you should not worry too much about that because this method will converge. So after doing all this, which is a very long process, we have to repeat it. So by these new values of R and S, so you will find the values of B and C coefficients again. Okay, we will find the B values of B and C coefficients again, and then you will solve a new set of these delta R and delta S equations. And then in the second step, we will find delta R will be this and delta S will be this. And then these will give us the new set of values for R and S. But in this case, we will find that the percentage error will reduce. So earlier it was from 50, now it is 26%. Previously, the percentage error in S was 800%, but now it is 70%. So the error has reduced, but still it is quite high. But again you have to perform this iteration. So it is found that after 4 iterations, yeah, so this was the second iteration, you will perform third, and then you will perform the second iteration, the error will reduce to less than 1%, 0.063% and 0.04%, with the resulting values of R equal to minus 0.5 and S is equal to 0.5. Okay, so very familiar values of minus 0.5 and 0.5 we will get. So these now these corrected values of R and S can be input into the quadratic formula for the equation x square minus rs minus s, and then we can find the two of the roots of the equations, which will be 0.5 and minus 1 in this case. So these are two of the roots, 0.5 and minus 1. Okay. So this is just one set of the solution, because we initially took the fifth order polynomial, right? So out of these fifth order polynomial, we have found two roots. So the other two roots we have to find it. But remember that now we have found the two roots. The other two roots will be the remaining three roots will be given by this equation, because now we have found the two of the roots, and then when we have found the two of the roots, then that means the b0 and b1 should be 0, and then to represent the 2-degree lower polynomial, we need the coefficients b2, b3, and bn. Okay, in this case, okay, b2, b3, and bn. So uh, then starting from b2, so that b2 will be the uh, lowest order polynomial in this case. So in this case, uh, yeah, in this case, when we get this result over here, 0 point and minus 0.15. In the previous case, we will get some of these coefficients over here. So for example, here. So in this case, the coefficients for the previous iteration, here, here, and here, these starting from B2 to B5, these coefficients will be the coefficients of the uh, third degree polynomial, will be the coefficients of the third degree polynomial. So that third degree polynomial then will be given by this equation. So we will get B2 is equal to this, we will get B3 is equal to this, we will get B4 is equal to this, we will get B5 is equal to this. And then if we input these coefficients, then we will get the third degree polynomial from the fifth degree polynomial over here. And then we have to repeat the same process. Okay. And in this case, what you can do is we can use the R and S values from the previous case. Although it is not necessary, but we can use the R and S values from the previous case and then repeat the same process. And in this case, the final R and S values will be 2 and minus 1.249, which will be actually 1.25. And then when you apply this into the quadratic formula, you will get uh, a complex solution, a complex conjugate solution, 1 plus minus 0.499i, or for an exact, in exact term, it will be 1 plus minus 0.5i. Okay, so from the third degree polynomial, then we can now reduce that polynomial to the single degree polynomial. And for that single degree polynomial, so we will need two coefficients that will be b0 and b4. Okay, and then b0 will be b5 and b4. Okay, so in that case, the coefficient b5 will be the coefficient b5 will be 1 and b0 will be minus 2. So in that, from there, that we can find the solution of the last last term that will be equal to 2. So this is how the Bairstow's method work, but it will be more, uh, it will be much clear if I show it on Excel to you. So I have created this Excel sheet for the Bairstow's method. Maybe let me, I have, it is the completed sheet. Maybe I can copy it. Okay, so this is the sheet. Okay, so in this, can you see this Excel sheet?
Yes.
Okay, so in this Excel sheet, this is the completed Excel sheet. So in this case, first of all, I have set up these variables, okay, in column A, starting from R and S. So in this case, initial values of R and S were -1 and -1. Remember that our equation was this. This was our equation. So fifth order polynomial equation. So this was the equation. Okay. So initially we chose and then we have to apply this equation. Mm, we have to apply this factor, r square minus rx is equal to s. Okay. So in this case, we need to assume the values of r and s. So we took the values of r and s as -1 and -1. Okay. And then we will calculate a5. So this a5 is calculated by the formula. Sorry, not calculated. This is, we don't need to calculate. Um, we need to calculate b, and we need to calculate b, and then we need to calculate c's. So if you have these formulas written down in front of you, then it becomes much easier. Okay, so next we will need to list the coefficients a5 to a0. Okay, so coefficients a5 to a0 will be the same. So for example, 1 minus 3.5, 2.75, these are the coefficients of the original equation. So 1 minus 3.5, 2.75, 2.125, and minus 3.875. And then from these coefficients, and then a naught is 1.25. And then from these coefficients, you will calculate, so for example, from these coefficients, you will calculate b coefficients. Okay, so these b coefficients will be here. And then from these coefficients, you will calculate, from the b coefficients, you will calculate c coefficients. But the c, in the c coefficients, there is no c0. Okay, c coefficients are from c1 to c5, b coefficients are from 0 to 5, and a coefficients are also from 0 to 5. Okay, so here, and then calculate the c coefficients, like here, give some other. Okay, c coefficients. So in this way, so these are given, these are calculated by these recursive formulas. Okay, and similarly, c coefficients are calculated by these recursive formulas. And then I applied the delta R and delta S. Okay, and then for this I have applied the Cramer's rule. Okay, so in the Cramer's rule, so you can write the equations in terms of these formats. Okay, so in this case, where is this equation? Yeah, so for delta R and delta S, you will use this equation. Okay, so in this case, what I will do is, so for example, delta R, I will use these values. So for example, it will be minus b1 times c2. Okay, so minus b1 is b16. Yeah, here minus b1 times c2 minus this one. Okay, and then plus uh, b naught times c3 plus b naught is b17. Okay, b17 times uh, the value in here, and then divided by this determinant. Okay, c2 square minus c1 c3. Okay. So in this way, then you will calculate this value of the delta r, and then similar way you can calculate the value of the delta s. So from the values of delta r and delta s, then you can calculate uh, then you can calculate r I plus 1, and then these are the revised values. So this value will be equal to r I plus 1 is equal to this initial value plus the delta r. Okay, and then s I plus 1 will be the initial s value plus delta s. Okay, and next you will calculate the percentage approximate error. Okay, by this will be delta r divided by this value multiplied by 100 and then taken in absolute terms. So in this case, the initial for the first iteration we get this value 55.25. So for the second iteration, now you will use these values for r and s which were found previously. So previously we have found these values minus 6.64 and plus 0.138. And then we have input these values over here. And now after that, I have just from here up to here, I have calculated, I have copied this value, and then from here up to here, I will have copied this value. So in this way, I did the how many iterations? Like so, this is the first iteration. This is the second iteration. This is the third iteration. This is the fourth, and this is the fifth iteration. So after 5 iterations, what I found that the percentage relative errors are this 1.3 into 10 to the power minus 5 and 2 into 10 to the power minus 6. So very close values. So these values are giving us the R and S values as minus 0.5 and 0.5. So when I input these values into the quadratic equation, okay, which was the quadratic equation? Quadratic equation was this. The quadratic equation was this. Yeah, so in this quadratic equation, then we got the value of x1 is equal to 0.5 and x2 is equal to minus 5, minus 1. So these are the two of the roots for this given equation. So we still have to find the other 3 roots. Okay, so for finding other 3 roots, then we should have the cubic equation. Okay, we should have the cubic equation. So in that cubic equations, we should have the coefficients a0, a1, a2, and a3. So these coefficients will be the same as in this last iteration, the coefficients for b2, b3, b4, and b5. Okay, b3. So we will copy these coefficients from here 1, 4, 5.25 minus 2.5 to here. Okay, and you can see that these are not very exact because this is the numerical method. There is a certain error, round of error over here. So we will input with these round of errors. So we have these coefficients a3 to a0, and then from these coefficients A3 to A0, we will find the coefficients B3 to B0. Okay, B3 to B0. And then from these coefficients B3 to B0, we will find the coefficient C3 to C1. Okay, C3 to C1. And then we will find by the same way delta R and delta S, and then Ri1 plus 1, and then Si1 plus 1. So in the initial estimate will give us the errors of 128 and 86%. And then by the later iterations, these errors will reduce, okay, from 128 to 4, and then little bit increase, but 4, and then gradually increasing. But by this, I don't know, maybe first, second, third, fourth, fifth, sixth, and seventh iteration, I get reasonably very close values over here. And then from this, the R and S values are 1.999, that is almost very near to 2, and this is equal to the value of S is equal to minus 1.2500. So from these two values, we find that this discriminant R square plus 4S is a negative term. So therefore, in this case, we will need to find the complex roots. Okay, so in previously we found the real roots. So we will in this case we will need to find the complex roots. So for the complex root, you can find the real part of the root, and you can also find the imaginary part of the root. So the real part of the root is R divided by 2. So simply take this value of R, and then you divide by 2. So that will be the real part of the root. And then the imaginary part of the root will be the square root of R plus 4S, and then we will take its absolute value of R square plus 4S, so that it becomes a positive value, and then you will take the square root and then divide it by 2. So this will be 0.5. So the answer over here, it will be actually 1 plus 0.5 I, and the other conjugate answer will be 1 minus 0.5 I. Okay, so these are the two complex roots over here. So now after previously we have found the two real roots. So from the two real roots, then we have reduced this equation to we have reduced this equation to a third degree equation. Okay, right? So what was that third degree equation? So this third degree equation was this. Let me copy it here. This third degree equation was this. Maybe here. So this was the third degree equation, okay? X cubed. And then this equation came from these coefficients, minus 2.5 right here, 5.25 here, minus 4 here, and then 1. So from these coefficients. And then from this third degree equation, now we will go to the first degree equation. And then this first degree equation will be the same as the coefficients of B3 and B2. So it will be 1 and 2. So that will be the equation x minus 2 is equal to 0. And from x minus 2 is equal to 0, we find that the fifth root will be, so the fifth, that means the final first degree equation is x minus 2 is equal to 0, and which gives that x is equal to x is equal to 2. So this is the fifth root. So simply we can find the fifth root from here. Okay, so because its coefficient is 1, the coefficient of x is 1, and the coefficient without the value of x power 0, it will be minus 2 from here. So does it explain the method in Excel?
Yes.
All right, so any questions about this method? Hello?
No questions. It's
No.
just too long.
Clear? Is it clear? Okay, so this was the Bairstow's method. Okay, so with this, I think the main part of this uh, topic on roots of the polynomials have been finished. So there were two main methods, Muller methods and the Bairstow method. So today we covered the Muller method. So for both for both Muller method and the Bairstow method, we also did it on Excel as well. So we know that how we can apply these methods on Excel as well. So similarly, there are other methods for the finding the roots of the polynomials. One of that method is called as the Jenkins-Straub method. It is a complicated method which is used in software libraries. Of course, this method has not been, it's just for the mention over here as well. If you want to try this method, then maybe you can go to the respective textbooks or books to find the details of this method. Another method is called as the Laguerre's method, which approximates both real and complex roots, and it takes the cubic convergence. And then, of course, we can use Excel to find the roots of the equations. There are three main approaches in Excel: trial and error, goal seek, and solver add-in. And then we can also use MATLAB functions such as F0 and the root function with the application of some other polynomial related functions to solve the uh, polynomial or other non-polynomial equations in MATLAB. So that's all for today. And then in the next class, we will have a review of the Excel and MATLAB methods approach. And then we will also start the next topic for the linear solution of numerical solutions for the system of linear equations. Okay, that's all for today.
Okay,